A drop of milk swirls into hot coffee, forming delicate white filaments. For a brief moment, complex patterns appear, eddies, curls, spirals, before everything blends into a uniform brown. No external force guides this process. No instruction tells the milk where to go, and yet the direction is unmistakable. The mixture never unmixes. That quiet, ordinary moment contains one of the deepest principles in all of physics. It reveals a direction built into reality itself. That direction is called entropy. At its core, entropy is a measure of possibility. It counts how many microscopic arrangements can exist beneath a system's visible appearance. When physicists talk about entropy, they are not talking about chaos, decay, or disorder in a casual sense. They are talking about numbers so large that they dwarf anything encountered in everyday life. Consider a box of gas. Macroscopically, it is described by temperature, pressure, and volume. These are simple, smooth quantities. But microscopically, the gas is a frenzy of motion. Trillions of particles flying, colliding, vibrating. Each exact specification of every particle's position and velocity defines a microstate. Many different microstates can look identical from the outside. The gas can have the same temperature and pressure, while its internal motions differ wildly. Entropy measures how many of these microstates correspond to the same macroscopic description. Low entropy means few compatible microstates. High entropy means many. This statistical definition is not philosophical. It is precise, measurable, and predictive. It explains why some processes occur spontaneously while others never do, even though the fundamental laws allow them. A crystal lattice has low entropy because its atoms occupy highly constrained positions. A gas evenly spread through a room has high entropy because there are astronomically many ways for particles to be distributed while still appearing uniform. The uniform state looks simple, but it hides enormous microscopic complexity. This insight transformed thermodynamics. In the 19th century, entropy was introduced as a bookkeeping tool to track heat flow in engines. It quantified how much energy became unavailable for useful work. Heat naturally flowed from hot objects to cold ones, and entropy increased as it did so. The law worked perfectly, but its deeper meaning remained hidden. Statistical mechanics revealed the secret. Entropy tracks probability. Systems evolve toward macrostates that can be realized in the greatest number of microscopic ways. No intention is required, no guiding hand is needed. Probability alone shapes the outcome. This statistical pressure explains why entropy gives rise to the arrow of time. The fundamental equations governing motion, classical mechanics, electromagnetism, quantum theory, are largely time-symmetric. If a process obeys these equations forward in time, it also obeys them backward. At the microscopic level, physics does not prefer past or future, yet the universe clearly does. Ice melts rather than refreezes spontaneously. Smoke disperses instead of gathering back into a cigarette. Stars exhaust their fuel and evolve toward colder remnants. The arrow of time emerges not from the laws themselves, but from the conditions under which the universe began. The early universe occupied an extraordinarily low entropy state. Matter and energy were distributed with astonishing uniformity, especially in the gravitational sense. From that rare starting point, almost every possible evolution leads toward higher entropy. The imbalance is overwhelming. For any low entropy configuration, there exist vastly more higher entropy configurations than lower ones. Once a system begins moving toward those more numerous states, the odds of reversing course become vanishingly small. This asymmetry explains irreversibility. Take a simple example: gas confined to one side of a container. Remove the barrier, and the gas expands to fill the available space. Every individual collision follows time-symmetric laws, yet the macroscopic outcome is one-directional. Before expansion, the gas occupied a highly constrained macrostate. After expansion, it occupies a vastly more probable one. Almost every microscopic trajectory leads toward the expanded state, because there are so many more ways to be expanded than confined. Reversal would require an extraordinary coincidence. Every particle would need to coordinate its motion with extreme precision. Such coordination is not forbidden, but it is so unlikely that it effectively never occurs. This is the essence of macroscopic irreversibility. It is not enforced by force or constraint, but by numbers. Large systems amplify probability into certainty. At the microscopic scale, motion appears chaotic and unpredictable. At the macroscopic scale, that same randomness produces stable, irreversible trends. Random collisions do not erase order directly. They funnel systems toward statistically dominant configurations. This perspective also clarifies a common misunderstanding. Entropy does not forbid order. Local decreases in entropy occur constantly. Refrigerators cool their interiors. Planets form from disks of dust. Living cells assemble intricate molecular machinery. These processes succeed because entropy is expelled into the environment. The second law applies globally. Total entropy increases when the entire system, including surroundings, is considered. Life is a striking example of this principle. Biological systems maintain low internal entropy by consuming energy gradients and releasing waste heat. Sunlight arrives at Earth in a low entropy form, concentrated and directional. It leaves as diffuse infrared radiation with higher entropy. Life exists not despite entropy, but because entropy production allows complexity to temporarily arise. As long as gradients exist, hot versus cold, concentrated versus dilute, processes can occur. When gradients disappear, activity ceases. This connects thermodynamic entropy to information. In information theory, entropy measures uncertainty. A highly ordered message carries little surprise. A random message carries much. Mathematically, this entropy is equivalent to thermodynamic entropy. Information is physical. Recording a memory, erasing a bit, transmitting a signal, all require energy and generate heat. When entropy increases, information about microscopic details becomes dispersed across many degrees of freedom. It is not destroyed, but it becomes inaccessible. This dispersion of information gives time its experiential direction. Records exist of the past: fossils, photographs, neural patterns, radiation backgrounds. These records persist because entropy increased during their formation, stabilizing them. Future states have no records yet because they have not been realized. High entropy states do not encode detailed histories. They retain outcomes, not pathways. Ash contains no blueprint of the flame. At cosmic scales, entropy growth becomes the dominant narrative. Stars convert low-entropy nuclear fuel into high-entropy radiation. Galaxies merge, randomizing orbital energy into heat. Black holes form, storing enormous entropy behind event horizons. Each step increases the universe's overall entropy budget. Even timekeeping depends on this process. Clocks rely on irreversible transitions. Observation requires energy flow. Memory formation depends on entropy increase somewhere in the system. Without entropy growth, nothing would register change. In this sense, entropy does not simply accompany time. It defines time's direction operationally. A universe at maximum entropy would still obey physical laws, but no process would distinguish one moment from the next. The journey toward heat death begins here, at this statistical foundation. Long before stars fade and galaxies drift beyond reach, the outcome is already written in probability space. Entropy steadily increases because higher entropy states dominate the landscape of possibility. The universe moves forward not because it must, but because almost every available path leads in that direction. And from this simple, unforgiving mathematics emerges the arrow that points everything, matter, memory, and meaning, toward a future that becomes ever harder to change. A fraction of a second after the universe began, everything that would ever exist was already present, compressed into a state hotter than any star, denser than any atomic nucleus, and expanding at a rate that would define the future of all cosmic structure. Temperatures soared to trillions of degrees. Particles collided relentlessly. Radiation dominated every interaction. And yet, despite this extreme heat, the universe began in a condition of astonishingly low entropy. At first glance, this sounds contradictory. Heat is often associated with disorder. A blazing furnace feels more chaotic than a frozen crystal. In everyday experience, hot systems tend to have higher entropy than cold ones. So how could the hottest state the universe ever experienced also be one of the lowest entropy states possible? The answer lies in what entropy actually counts, and in the unique role gravity plays at cosmic scales. In non-gravitational systems, such as gases in a box, high entropy corresponds to uniformity. When particles are evenly distributed, entropy is high because there are many microscopic arrangements that produce that same smooth appearance. When particles are clumped into one corner, entropy is low. Gravity reverses this intuition. Under gravity, uniformity is rare and special. Matter naturally wants to clump. Given enough time, gravity pulls mass together into stars, galaxies, and black holes. A smooth, evenly distributed universe is not the gravitationally favoured outcome. It is the improbable one. The early universe was extraordinarily smooth. Matter and energy were spread out with incredible uniformity, differing in density by only 1 part in 100,000. This smoothness was not a sign of high entropy, it was a sign of extreme constraint. Gravitational entropy was extraordinarily low. To understand this, imagine spreading sand evenly across a table. That smooth layer looks simple, but it represents a very specific arrangement. If you shake the table, sand naturally forms piles and patterns. The clumped state is far more probable than the perfectly even one. The early universe was like a cosmic tabletop covered with perfectly leveled sand, except the table was space-time itself and the sand was everything. This gravitational smoothness is the key to understanding why the universe started with low entropy despite its heat. Thermodynamically, the universe was near equilibrium. Particles and radiation exchanged energy rapidly. Temperatures were nearly uniform. From a non-gravitational perspective, entropy was already high. But gravity changes the accounting. A universe where matter is evenly spread has very few gravitational microstates. A universe filled with stars, galaxies, clusters, and black holes has vastly more. As structure forms, gravitational entropy increases dramatically. This means the early universe possessed an enormous entropy gap, a vast capacity for entropy growth that would fuel all future cosmic evolution. Expansion played a critical role in preserving this low entropy condition. As the universe expanded, it cooled. Energy densities dropped, interactions slowed. Expansion acted like a cosmic decompression, preventing the system from immediately collapsing into higher entropy gravitational states. At the same time, expansion stretched tiny quantum fluctuations, minute variations in density generated in the earliest moments, into macroscopic seeds for future structure. These fluctuations were small enough to maintain overall smoothness, yet large enough to eventually grow under gravity. This delicate balance mattered enormously. If the early universe had been even slightly more irregular, gravity would have caused rapid collapse into black holes. If it had been perfectly uniform with no fluctuations at all, structure would never have formed. No stars, no galaxies, no chemistry. The universe began in a narrow corridor between chaos and stagnation. As expansion continued, gravity slowly gained leverage. Regions slightly denser than average began to pull in surrounding matter. Over hundreds of millions of years, these regions collapsed into the first stars and galaxies. This process marked a crucial transition. Structure formation increases entropy, but not immediately in the most obvious way. When matter collapses under gravity, it initially appears to become more ordered. Gas clouds form rotating disks, stars ignite in well-defined spheres, galaxies take on elegant spiral shapes. From a visual standpoint, the universe looks more structured, not less. But entropy accounting does not care about appearance. It cares about accessible microstates. Gravitational collapse converts potential energy into heat and radiation. As gas falls inward, it heats up. As stars form, nuclear fusion releases vast amounts of energy into surrounding space. Radiation streams outward, dispersing energy across enormous volumes. The local system becomes more ordered, but the universe as a whole gains entropy. This is why structure formation can be thought of as a temporary delay, not a reversal of entropy's rise. Gravity creates pockets where complexity increases locally, but only by accelerating entropy production globally. Stars are entropy engines. They take low-entropy fuel, hydrogen nuclei arranged in a diffuse gravitational field, and convert it into high-entropy radiation emitted into the cold darkness of space. Every photon escaping a star carries entropy with it. Over time, this process dominates the universe's entropy budget. Galaxies, too, are transient. Their ordered rotation masks an underlying trend toward energy dispersal. Collisions between galaxies randomize stellar orbits. Gas heats and radiates. Eventually, star formation slows as fuel is exhausted. Throughout this era, the universe remains far from equilibrium. Temperature gradients exist, energy flows, complexity thrives. All of this is possible because the early universe began so far from gravitational equilibrium. The arrow of time at cosmic scales originates here. The reason entropy increases today is not because the universe is cooling or expanding alone. It increases because the universe began in a special state that allowed entropy to grow. This raises a deep question. Why was the early universe so smooth? Modern cosmology describes this smoothness with extraordinary precision, but its ultimate origin remains an open problem. Inflationary models explain how small fluctuations could be stretched to cosmic scales, producing uniformity across vast regions. Yet inflation itself requires finely tuned initial conditions. The low entropy of the early universe is not explained by known physical laws alone. It is a boundary condition, a starting point that sets the direction of time for everything that follows. Once this starting point is accepted, the rest unfolds with statistical inevitability. As structures form, entropy rises. As stars burn, entropy rises faster. As black holes emerge, entropy skyrockets. The universe moves steadily towards states that occupy more and more of the available phase space. And yet, for billions of years, structure formation slows this march just enough to allow complexity to exist. Planets form around stars. Chemistry builds molecules. Biology exploits energy gradients. Conscious observers arise, capable of reconstructing the universe's past precisely because entropy has increased in just the right way. This window is temporary. Structure formation cannot continue indefinitely. Expansion eventually isolates galaxies. Star formation peaks and declines. Gravitational clumping reaches its limits. When the last stars fade, the entropy gap created by the early universe's smoothness will finally be nearly exhausted. But all of that future, every galaxy, every atom, every thought, traces back to this improbable beginning. A universe that was blisteringly hot, astonishingly uniform, gravitationally smooth, and profoundly low in entropy. That initial condition did not merely set the stage for cosmic history. It wrote the direction of time itself. A star shines because its core is hotter than the space around it. A river flows because its source sits higher than its mouth. A thought forms in the brain because chemical concentrations differ across a membrane by tiny but crucial amounts. Every process that does anything at all depends on one simple condition: a difference. In physics, that difference is called an energy gradient. An energy gradient exists whenever energy is unevenly distributed, when one region is hotter than another, denser than another, more concentrated, more ordered, or more energetic in a way that can be exploited. Gradients are not side effects of activity, they are the cause of activity. Without them, nothing moves, nothing changes, nothing happens. The universe is active today only because it is still profoundly uneven. Stars burn because nuclear energy is concentrated in their cores while surrounding space is cold and empty. Life persists because chemical energy inside cells is organized and separated from the environment. Chemistry occurs because electrons occupy higher energy configurations that can relax into lower ones. Motion itself depends on differences in potential, gravitational, electrical, or thermal. Remove gradients and the universe becomes perfectly still. This is why gradients sit at the heart of thermodynamics and why entropy matters so deeply. Entropy increases because gradients are consumed. The arrow of time points in the direction gradients are flattened. To understand why complexity exists at all, we must understand how gradients create usable energy and why equilibrium represents the end of that story. In thermodynamics, not all energy is equal. Total energy is always conserved, but only a fraction of it can perform work. That is, produce organized motion, change, or structure. This usable portion is called free energy. Free energy exists only when a system is out of equilibrium. A hot object in a cold room has free energy because heat can flow outward and do work. Drive engines, power chemical reactions, generate motion. Once the room and the object reach the same temperature, the energy is still there, but it is no longer usable. The gradient has vanished. This distinction explains why equilibrium is not a dramatic collapse, but a quiet ending. Nothing breaks. Nothing explodes. The system simply loses its capacity to change in interesting ways. At equilibrium, entropy is maximized and free energy is minimized. The universe began with an enormous supply of free energy locked into gradients created by expansion, gravity, and the separation of forces. Ever since, cosmic history has been the story of how that free energy is spent. Stars are among the most spectacular gradient-exploiting machines ever produced. A star forms when gravity pulls gas together, converting gravitational potential energy into heat. As the core compresses, temperature rises until nuclear fusion ignites. Hydrogen nuclei fuse into helium, releasing energy because the resulting nucleus has lower mass energy than its components. This energy flows outward from the core to the surface and then radiates into space. The star exists because there is a steep gradient between its hot interior and the cold cosmic background. That gradient drives radiation, stellar winds, convection, and nuclear reactions. Every second, the star reduces that gradient slightly by dumping energy into space. The star does not resist entropy, it accelerates it. Yet in doing so, it creates new gradients elsewhere. Starlight strikes planets, creating temperature differences between day and night, equator and pole, surface and atmosphere. These gradients drive winds, weather, ocean currents, and chemical cycles. On at least one planet, they also drive life. Life is not an exception to thermodynamics, it is a direct consequence of it. Living systems exist only because they sit between strong gradients. Earth receives low entropy energy from the sun in the form of visible light, highly directional, concentrated and structured. It emits higher entropy infrared radiation back into space, diffuse, isotropic, and information poor. Life operates in the middle, extracting free energy from this flow. Inside a cell, gradients are everywhere. Proton concentrations differ across membranes. Electrical potentials are carefully maintained. Molecules exist in unstable configurations, ready to react. These gradients allow cells to synthesize complex molecules, copy information, and maintain internal order. None of this violates the second law of thermodynamics. The cell lowers its own entropy by increasing the entropy of its surroundings even more. Life persists only as long as the gradients persist. This principle scales upward. Ecosystems depend on solar gradients. Climate systems depend on uneven heating. Geological activity depends on temperature differences inside planets. Even human technology, from engines to computers, functions by exploiting gradients and dumping waste heat. Every machine is an entropy generator. This connection between gradients and entropy production reveals something crucial. Complexity is not the opposite of entropy increase. It is one of entropy's most efficient pathways. Systems that form organized structures often do so because those structures accelerate the dissipation of gradients. A hurricane forms because it transports heat from warm ocean surfaces to cooler upper atmospheres more efficiently than random motion could. A star forms because it allows gravitational energy to be converted into radiation more effectively. Complexity arises because it helps gradients disappear faster. This idea reframes the rise of structure in the universe. Galaxies, stars, planets, and life are not improbabilities fighting against thermodynamics. They are natural outcomes of a universe far from equilibrium, temporarily rich in free energy. But gradients are finite. Every gradient is a slope that eventually flattens. Heat flows until temperatures equalize. Chemical reactions proceed until reactants are exhausted. Gravitational collapse proceeds until stable configurations, or black holes, form. As gradients weaken, the capacity for work declines. This is why equilibrium represents the end of complexity. In a universe at thermal equilibrium, energy is evenly distributed. Every region has the same temperature. No net heat flow exists. Without heat flow, engines cannot operate. Without free energy, chemistry stalls. Without chemistry, life becomes impossible. Without irreversible processes, time loses operational meaning. Equilibrium is not cold or dark by necessity. It is inactive. Even motion ceases to matter. Particles may still move randomly, but their motion produces no macroscopic change. No pattern grows, no memory forms, no structure persists against fluctuations. The universe becomes a place where nothing interesting can happen, not because laws disappear, but because the conditions required for change are gone. Importantly, the universe is nowhere near this state yet. Cosmic gradients remain enormous. Stars still burn, black holes still accrete, galaxies still collide. Temperature differences exist across vast scales. The cosmic microwave background itself remains slightly warmer than the future universe will be. But the direction is fixed. Every star that shines reduces nuclear gradients. Every photon emitted spreads energy thinner. Every collision randomizes motion. Every process that creates structure also drains the supply that made it possible. This is why heat death is not a sudden catastrophe, but a slow fading. As gradients diminish, the universe does not collapse. It relaxes. Star formation slows as gas becomes scarce. Galaxies age into quieter configurations. Matter settles into long-lived remnants, white dwarfs, neutron stars, black holes. Radiation stretches to longer wavelengths as space expands. Each step brings the universe closer to equilibrium, and once equilibrium is reached, complexity has no foothold left. No gradients mean no free energy. No free energy means no work. No work means no change worth naming. The engine of activity stalls not because the universe breaks, but because it succeeds, because it finishes. The job entropy began at the very beginning. The story of the universe from blazing stars to silent darkness is ultimately the story of gradients being spent. And everything that has ever moved, lived, or thought has done so by borrowing time from that finite supply. Space itself is growing. Not objects moving through space, not galaxies flying away from a central point, but the fabric of distance expanding between everything. Every second, the gaps between galaxy clusters widen. Every moment, wavelengths stretch. Every passing epoch, the universe becomes larger, emptier, and colder. Not because matter is being removed, but because space-time is being pulled taut. This expansion is one of the most powerful engines shaping the universe's future, and it plays a decisive role in the long journey toward heat death. To understand why, it helps to start with a simple but often misunderstood idea. Cosmic expansion does not happen inside space, it happens to space. On small scales, gravity and electromagnetic forces dominate. Atoms remain intact. Solar systems stay bound. galaxies hold together. Expansion becomes noticeable only across vast distances, where gravity weakens and space-time's overall behaviour takes over. At those scales, expansion is relentless. Galaxies recede from one another because the metric that defines distance is changing. Light travelling through space is stretched along with it, increasing its wavelength and lowering its energy. Over cosmic time, this stretching steadily drains usable energy from the universe. For much of cosmic history, expansion slowed down. Matter and radiation exerted gravitational attraction, tugging space-time inward and decelerating the growth of distances. In that era, structure formation thrived, galaxies formed, clusters assembled, stars ignited in abundance. Then, several billion years ago, something remarkable happened. Expansion began to accelerate. This acceleration revealed the presence of dark energy, a component of the universe that does not clump, does not dilute significantly as space expands, and exerts a persistent outward influence on space-time itself. Dark energy is not a force in the usual sense. It behaves more like a property of space, an energy associated with the vacuum. As space grows, more vacuum appears. As more vacuum appears, more dark energy exists. The result is a feedback loop. Expansion creates conditions that promote further expansion. The effect is subtle on human timescales, but overwhelming on cosmic ones. Accelerated expansion reshapes the universe's long-term thermodynamic fate by doing three crucial things. It stretches energy gradients thinner, it isolates regions of space from one another, and it enforces a steady march toward equilibrium that no local process can reverse. Consider light. Every photon travelling through expanding space loses energy as its wavelength stretches. This process, known as cosmological redshift, does not transfer energy to anything else. The energy simply becomes less concentrated, spread over longer wavelengths. From a thermodynamic perspective, this is pure entropy production. High-energy photons become lower-energy photons. Directional information-rich radiation turns into diffuse, low-energy background glow. Over time, all radiation trends toward longer wavelengths, approaching the coldest possible state permitted by expansion. Matter suffers a similar fate. As expansion accelerates, galaxies outside our local gravitational neighborhood recede faster and faster. Eventually, their recession speed exceeds the speed at which light emitted today could ever reach us. These galaxies cross a boundary known as the cosmic event horizon. Once beyond this horizon, causal contact is lost forever. Signals sent from here will never arrive there. Signals sent from there will never arrive here. The universe fractures into isolated islands of matter, each surrounded by an ever-growing sea of empty space. This isolation has profound implications for entropy. In a connected universe, energy can flow from one region to another. Hot systems can radiate into colder ones. Matter can fall into deeper gravitational wells. Gradients can be rearranged, exploited, and dissipated efficiently. Accelerated expansion shuts these channels down. As galaxies slip beyond causal contact, the universe loses the ability to redistribute energy across large scales. Each island evolves in near isolation, consuming its internal gradients without replenishment. Expansion does not merely allow entropy to increase, it prevents entropy from being undone by cutting off pathways that might otherwise sustain complexity longer. Within gravitationally bound regions, processes continue for a time. Stars burn, black holes grow, matter interacts, but the larger cosmic context grows increasingly irrelevant to local physics. The universe becomes a collection of disconnected thermodynamic experiments, each running down on its own finite supply of free energy. Expansion also undermines gravity's long-term role. Gravity thrives on density. It pulls matter together, creating structure and increasing gravitational entropy through clumping. But expansion thins matter out. As space stretches, average densities fall. Structures stop forming once matter becomes too dilute to collapse further. This marks the end of cosmic construction. Star formation peaks, then declines. Gas reservoirs become exhausted or too diffuse to ignite new stars. Galaxies age into populations dominated by stellar remnants. Gravitational interactions slow as distances increase. Expansion does not stop entropy production. It changes its character. Early in cosmic history, entropy increased rapidly through structure formation and star birth. Later, entropy increases through radiation, particle decay, and the slow fading of bound systems. Expansion ensures that no new large-scale gradients emerge to replace the old ones. Even black holes, the most extreme entropy reservoirs known, exist within this expanding context. Hawking radiation leaks energy from their event horizons at an almost unimaginably slow rate. Expansion stretches that radiation further, lowering its energy and dispersing it into an ever-growing volume. Expansion guarantees that once energy is spread thinly enough, it stays that way. This is why accelerated expansion plays such a decisive role in the universe's long-term thermodynamics. It enforces irreversibility on the largest possible scale. In a universe without acceleration, distant regions could remain in causal contact indefinitely. Matter might continue to clump slowly. Energy gradients might persist longer. Entropy would still increase, but the journey toward equilibrium would be less direct. Dark energy changes that trajectory. By accelerating expansion, it ensures that the universe becomes colder, emptier, and more isolated with time. Energy becomes less accessible. Interactions become rarer. The conditions required for complexity fade not because they are forbidden, but because they become increasingly improbable. From the perspective of entropy, expansion acts like a vast dilution engine. Every cubic meter of space added to the universe lowers the average energy density. Every stretched wavelength lowers the temperature of radiation. Every receding galaxy reduces the pool of accessible matter. Entropy still increases, but free energy, the portion that can do work, shrinks relentlessly. Eventually, expansion dominates everything. The cosmic microwave background cools toward absolute zero as wavelengths stretch beyond detectability. Particles drift farther apart, interactions becoming vanishingly rare. Even time itself loses practical meaning as change slows to a crawl. In this far future, expansion has accomplished what no explosion or collapse ever could. A smooth, quiet erasure of gradients across the largest scales imaginable. The universe does not end in fire or ruin, it thins. Dark energy does not destroy structure violently. It simply denies structure the conditions it needs to persist. By isolating regions of space and stretching energy ever thinner, expansion ensures that entropy's rise faces no meaningful opposition. The road to heat death is long, unimaginably long, but its direction is set. Cosmic expansion stretches space-time, redshifts energy, isolates matter, and locks the universe into a future where equilibrium becomes unavoidable. Every passing billion years makes gradients weaker, interactions rarer, and complexity harder to sustain. In the end, expansion becomes the quiet architect of silence, guiding the universe toward a state where nothing remains uneven enough to change. Every point of light in the night sky is a clock. Each star measures time not with ticking hands, but with nuclear fuel. With every second that passes, hydrogen is fused into heavier elements, energy escapes into space, and the star moves, slowly, irreversibly, toward a quieter state. Multiply this process by hundreds of billions of stars per galaxy, across trillions of galaxies, and stellar aging becomes one of the dominant forces shaping the universe's long-term future. Starlight feels permanent on human timescales. Constellations barely change. The sun rises reliably each day. But on cosmic timescales, stars are temporary structures, bright interruptions in a universe gradually learning how to go dark. The decline of starlight is not sudden, it is methodical, governed by well-understood physics, and already far underway. Star formation reached its peak billions of years ago. Observations of distant galaxies, seen as they were in the past due to the finite speed of light, reveal that the universe was once far more productive. Roughly 10 billion years ago, galaxies were converting gas into stars at rates several times higher than today. Since then, the cosmic star formation rate has been falling. The reason is not mysterious. Stars require cold, dense gas to form. That gas is finite. Every generation of stars consumes part of it, locking matter into long-lived stellar remnants, or dispersing it into hot, diffuse environments where it becomes harder to recycle. At the same time, cosmic expansion stretches gas clouds apart, lowering their density and suppressing collapse. Galaxies are slowly running out of raw material. Some still form stars actively, especially spiral galaxies rich in gas. Others, like massive ellipticals, exhausted their supplies long ago and now consist almost entirely of aging stars. Even in the most productive regions, star formation today is a shadow of its former intensity. This decline marks the beginning of the universe's long stellar sunset. Not all stars age the same way. A star's fate is determined primarily by its mass, and mass dictates both how brightly it shines and how quickly it spends its fuel. Massive stars burn fast and die young. Small stars burn slowly, conserving their energy with extraordinary patience. The most common stars in the universe are red dwarfs, small, cool stars with masses far below that of the Sun. Individually faint, collectively dominant, red dwarfs account for the majority of all stars ever formed. Their low mass allows them to burn hydrogen at a leisurely pace, stretching their lifetimes to trillions of years, far longer than the universe has existed so far. Red dwarfs represent the long tail of stellar activity. Long after stars like the Sun have faded, red dwarfs will continue to glow dimly, providing the last steady sources of starlight in the cosmos. Stars like the Sun follow a different path. After billions of years fusing hydrogen in their cores, they exhaust their central fuel supply. The core contracts and heats up while the outer layers expand dramatically. The star becomes a red giant, shedding material into space and enriching its surroundings with heavier elements. Eventually, the outer layers drift away, leaving behind a dense core known as a white dwarf. White dwarfs are stellar embers, objects roughly the size of Earth but containing a mass comparable to the Sun. No nuclear fusion occurs within them. They shine only because they are hot, gradually radiating their stored thermal energy into space. Over immense spans of time, white dwarfs cool, their light dims, their temperature drops. In the distant future, they become cold, inert objects, sometimes called black dwarfs, though none exist yet, because the universe has not been old enough for this process to complete. More massive stars meet more dramatic ends. Stars several times heavier than the Sun fuse heavier elements in successive stages, building onion-like cores of increasingly massive nuclei. This process ends abruptly when fusion reaches iron, which cannot release energy through further fusion. At that point, the star's core collapses under gravity, triggering a supernova explosion. The outer layers are blasted into space, while the core compresses into a neutron star, or, if massive enough, a black hole. Neutron stars are among the densest objects in the universe. A single teaspoon of neutron star matter would weigh billions of tons. These objects spin rapidly, emit intense radiation, and possess magnetic fields trillions of times stronger than Earth's. Yet even neutron stars are not eternal. Over incomprehensibly long timescales, they cool, spin down, and fade into darkness. Black holes represent the most extreme endpoints of stellar evolution. Formed when gravity overwhelms all other forces, black holes lock matter and energy behind event horizons. They grow by accreting surrounding material and by merging with other black holes. In terms of entropy, black holes are extraordinarily significant. They contain far more entropy than ordinary matter. For a time, black holes shine indirectly through accretion disks and jets. But once surrounding matter is consumed or expelled, they become dark, silent gravitational wells. the universe eventually enters what can be called the stellar remnant era, a time dominated not by shining stars, but by the leftovers of stellar evolution. As star formation continues to decline, new stars become rarer, existing stars age and die. Galaxies transition from bright dynamic systems to collections of dim, slowly evolving objects. The final era of star birth is difficult to define precisely, but the trend is clear. As gas becomes scarce and expansion accelerates, the conditions required for star formation vanish. Eventually, no region remains dense enough to collapse into new stars. When the last star forms, the universe does not notice. No alarm sounds, no cosmic event marks the moment. Star formation simply fails to occur again. From that point forward, the universe's light budget becomes strictly finite. Every photon emitted afterward comes from existing stars, cooling remnants, or exotic processes like black hole evaporation. Darkness does not arrive all at once. It deepens gradually. Red dwarfs linger, providing faint illumination for trillions of years. White dwarfs glow weakly as they cool. Neutron stars emit residual heat. Occasional collisions release bursts of energy, but each source is weaker than the last. Starlight becomes increasingly rare, increasingly redshifted, increasingly diluted by expansion. Eventually, even the longest-lived stars exhaust their fuel. Red dwarfs, despite their longevity, are not immortal. When their hydrogen supply finally dwindles, they too fade into dark remnants. At that stage, galaxies consist almost entirely of cold stellar corpses and black holes drifting through expanding space. No new nuclear reactions occur, no fresh starlight is born. The universe enters a prolonged twilight, a time measured not in billions, but in trillions of years. This slow extinction of starlight has profound thermodynamic consequences. Stars are among the universe's most efficient entropy producers. By converting concentrated nuclear energy into diffuse radiation, they drive the universe toward equilibrium. As stars disappear, entropy production slows, but it does not stop. Radiation already emitted continues to redshift and spread. Matter continues to cool. Black holes quietly dominate the entropy budget. The fading of starlight marks the transition from an active luminous universe to a passive, aging one. Complexity becomes harder to sustain. Without abundant energy sources, chemical and biological processes lose their foundation. Any remaining complexity must rely on dwindling gradients, becoming ever more fragile. Yet the universe does not end with the last star. Darkness is not an endpoint, but a condition. In the absence of starlight, the universe still evolves, slowly, subtly, inexorably. Black holes persist. Particles decay, space continues to expand. Entropy continues its steady climb. Stellar aging is not a tragedy written into the cosmos. It is a consequence of finite fuel and statistical law. Stars shine because they can. They fade because they must. The night sky's brilliance is a temporary phase in a universe learning how to rest. Long after the last stars have formed, the universe does not become empty. It becomes quietly solid. The sky no longer glows with nuclear fire, but matter remains, compressed, cooled, and locked into forms that barely change. These objects no longer shine because energy flows through them. They persist because nothing remains energetic enough to disturb them. This is the era of degenerate matter. Degenerate matter is not defined by temperature or chemistry, but by quantum mechanics. It arises when gravity compresses matter so intensely that the familiar rules of pressure and heat no longer apply. Instead, stability comes from quantum limits, fundamental restrictions on how closely particles can be packed. These limits create the last stable objects the universe knows how to make. The most common of these remnants are white dwarfs. A white dwarf is the exposed core of a star like the Sun, left behind after its outer layers drift away. It contains roughly the mass of the Sun squeezed into a sphere about the size of Earth. In this extreme environment, electrons are forced into the smallest possible volume allowed by quantum mechanics. What supports the star is not heat, fusion, or radiation pressure. It is electron degeneracy pressure, a quantum effect arising from the Pauli exclusion principle, which prevents electrons from occupying identical states. As long as this limit holds, the white dwarf remains stable. When a white dwarf forms, it is intensely hot. Temperatures can exceed 100,000 degrees, but this heat is residual. No new energy is being generated. The white dwarf shines only because it is cooling, and cool it does. Over trillions of years, a white dwarf radiates away its stored thermal energy. Its glow fades from white to yellow, to red, to infrared. Eventually, its temperature approaches that of its surroundings. At that point, it becomes what astronomers call a black dwarf. Not a black hole, not a collapsed object, but a cold, dark, stellar ember. No black dwarfs exist yet. The universe is still too young. Even the oldest white dwarfs have not had enough time to cool completely. But given enough time, far more than the current age of the universe, this outcome is unavoidable. Black dwarfs represent matter in a profoundly inert state. They do not burn, they do not glow, they do not evolve meaningfully. Their internal structure remains frozen, supported entirely by quantum pressure. In a dark future universe, black dwarfs may outnumber shining stars by enormous margins. Some white dwarfs do not remain solitary. In rare cases, gravitational interactions cause collisions or mergers between them. When two white dwarfs merge and exceed a critical mass, electron degeneracy pressure fails. The result can be a catastrophic thermonuclear explosion, a type I, a supernova. But these events become increasingly rare as the universe expands and stellar remnants drift farther apart. Eventually, mergers cease almost entirely. White dwarfs settle into long-term isolation. More extreme remnants exist as well. When massive stars collapse, their cores may compress beyond electron degeneracy, forcing electrons and protons to combine into neutrons. The result is a neutron star, an object so dense that atomic structure dissolves into a sea of neutrons. Neutron stars are supported by neutron degeneracy pressure, along with strong nuclear forces. They are typically only about 20 kilometers across, yet contain more mass than the Sun. Their gravity is intense. Their magnetic fields are immense. Their rotation can be astonishingly fast. Initially, neutron stars are energetic. They emit radiation, beams of particles, and thermal heat. Over time, these emissions fade. Neutron stars cool. As they cool, their activity slows, rotation decays, magnetic fields weaken, emission becomes negligible. Eventually, a neutron star becomes a dark, inert object, still dense, still massive, but no longer dynamic. The long-term fate of neutron stars depends on a deeper question in physics. Is matter truly stable? Protons, which make up atomic nuclei, are extraordinarily long-lived. Experiments have never observed a proton decay event, but many theoretical models suggest that protons may not be absolutely stable. Their lifetimes, if finite, are staggeringly long, far exceeding the age of the universe so far. If proton decay occurs, even rarely, its implications are profound. In a universe where protons decay, all baryonic matter is temporary. Over immense spans of time, protons would spontaneously transform into lighter particles, releasing energy in the process. Atoms would dissolve, nuclei would fall apart. Neutron stars and white dwarfs would slowly lose mass from within. This would not happen explosively. It would happen silently, particle by particle, over timescales measured in billions of years. A neutron star experiencing proton decay would gradually soften. As its mass decreases, the delicate balance supporting it changes. Eventually, it may expand slightly or disperse, releasing its remaining energy as low-level radiation. White dwarfs would similarly erode, their degenerate matter slowly converting into radiation and lighter particles. If proton decay does not occur, matter becomes even more stubbornly persistent. White dwarfs and neutron stars would remain intact far longer, evolving only through rare gravitational interactions or quantum processes. Either way, matter becomes increasingly inert. The universe transitions from a place where change is driven by energy flow to one where change is driven by chance. Collisions between remnants become the primary remaining source of activity. Over enormous timescales, gravitational encounters can cause objects to merge or be ejected from galaxies. Some remnants may fall into black holes, others may wander alone through intergalactic space. But these events become vanishingly rare as expansion stretches space and isolates matter. Black holes represent the most extreme degenerate objects. They are not supported by degeneracy pressure in the traditional sense, but they are endpoints of collapse where no known force can halt gravity. Black holes dominate the entropy budget of the universe because their event horizons encode enormous numbers of microstates, yet even black holes are not truly permanent. Over timescales far exceeding those associated with stellar remnants, black holes lose mass through quantum processes at their horizons. Hawking radiation slowly leaks energy away, causing black holes to evaporate. For stellar mass black holes, this process takes vastly longer than the current age of the universe. For supermassive black holes, the timescales are almost beyond language. But evaporation proceeds nonetheless. In the far future, after stars have faded and remnants have cooled, black holes become the last significant engines of change, quietly converting mass into diffuse radiation. Before that final stage arrives, the universe spends an enormous duration dominated by degenerate matter. This is not a dynamic epoch, it is a holding pattern. Matter is locked into quantum-supported configurations that resist further transformation. Temperature differences are small, energy gradients are weak, processes unfold with extreme slowness, complexity becomes fragile. Any remaining structure must rely on rare interactions or the slow decay of particles. Chemistry, as once known, no longer functions. Life, if it exists at all, must operate under constraints so severe that it bears little resemblance to earlier forms. Entropy continues to increase, but at a reduced pace. The universe has not reached equilibrium yet, but it is approaching it asymptotically. Degenerate matter represents matter at its most exhausted. It has fallen as far as it can without crossing into complete dissolution. It remains because the universe has not yet found a way to erase it efficiently. Eventually, even this resistance yields. If protons decay, matter dissolves from within. If black holes evaporate, mass turns into radiation. If expansion continues, radiation thins toward nothingness. Degenerate matter does not mark the end of cosmic evolution. It marks the end of active matter. From this point forward, the universe's story is no longer about structure forming, but about structure slowly unraveling. One particle, one quantum event, one unimaginably long interval at a time. The universe becomes a place where matter still exists, but almost nothing happens. And that silence is not imposed, it is earned. A region of space grows so dense that even light cannot escape. Orbits disappear. Directions lose meaning. What remains is not simply an object, but a boundary, a surface beyond which the universe refuses to answer questions. That boundary is the event horizon of a black hole. Black holes are often described as cosmic monsters or destructive sinks, but from the perspective of physics, they are something far more subtle and far more important. They are the universe's most efficient containers of entropy. More than stars, more than galaxies, more than all ordinary matter combined, black holes dominate the accounting of disorder, information, and irreversibility. They are not just endpoints of collapse, they are entropy's ultimate vaults. To see why, we must return to what entropy actually measures. Entropy counts how many microscopic configurations correspond to the same macroscopic description. The higher the entropy, the more hidden complexity lies beneath a simple exterior. A system with maximal entropy stores vast amounts of information in forms that are inaccessible at the macroscopic level. Black holes push this idea to its absolute limit. From the outside, a black hole appears astonishingly simple. Once formed, it can be fully described by just a few quantities: mass, electric charge, and angular momentum. All other details, the composition of what fell in, the arrangement of particles, the structure of collapsing matter, vanish from view. This simplicity is deceptive. Behind the event horizon, the number of possible microscopic states consistent with that simple exterior description is enormous. In fact, it is larger than for any other object of comparable size and mass. This realization marked one of the deepest breakthroughs in theoretical physics. In the 1970s, physicists discovered that black holes obey thermodynamic laws. They possess temperature, they radiate energy, and most strikingly, they have entropy. An entropy proportional not to their volume, but to the area of their event horizon. This result was astonishing. In ordinary systems, entropy scales with volume because particles occupy three-dimensional space. For black holes, entropy scales with surface area. This implies that all the information about the interior is somehow encoded on the horizon itself. The event horizon acts as a physical ledger, recording the possible internal states of the black hole without revealing them. The amount of entropy stored is staggering. A single stellar mass black hole contains vastly more entropy than an entire star before collapse. A supermassive black hole at the center of a galaxy contains more entropy than all the stars in that galaxy combined. In fact, supermassive black holes dominate the entropy budget of the observable universe by many orders of magnitude. Most of the universe's entropy is already locked behind event horizons. Why is black hole entropy so large? Because black holes represent the most extreme compression of matter allowed by physics. When matter collapses into a black hole, its degrees of freedom, positions, momenta, quantum states are packed into the smallest possible region consistent with the laws of space-time. Every additional bit of mass added to a black hole increases the area of its horizon, and with it, the number of microscopic configurations the interior can take. Entropy increases not because black holes are chaotic, but because they hide complexity perfectly. The event horizon plays a crucial role in this hiding. An event horizon is not a physical surface. Nothing tangible exists there, yet it marks a boundary of causal influence. Events inside the horizon cannot affect the outside universe. Signals cannot cross outward. Information, once passed inward, is no longer accessible to external observers. From the outside, information appears to be lost. This apparent loss troubled physicists deeply. The fundamental laws of quantum mechanics insist that information is conserved. Processes may scramble information, but they cannot erase it completely. Black holes seem to violate this principle. This tension became known as the black hole information problem. The resolution that emerged reshaped our understanding of entropy and spacetime. Information is not destroyed by black holes. It is encoded in subtle correlations associated with the event horizon and eventually with the radiation emitted as black holes evolve. From a thermodynamic standpoint, what matters is that information becomes inaccessible. Entropy measures precisely this inaccessibility. When information is hidden behind a horizon, it contributes to entropy because it can no longer be used to do work, reconstruct past states, or influence future dynamics. Black holes are entropy-rich because they are information-sealed. As the universe evolves, black holes form naturally from the deaths of massive stars and from the mergers of galaxies. Over time, smaller black holes collide and merge, producing larger ones. Each merger increases total entropy dramatically. Entropy always increases in black hole mergers. The area of the final event horizon exceeds the sum of the areas of the original horizons. This rule mirrors the second law of thermodynamics and elevates it to a geometric principle of space-time itself. The universe, through gravity, actively constructs larger and larger entropy reservoirs. This has profound implications for cosmic evolution. Early in the universe, entropy increased rapidly through star formation, radiation, and structure formation. Later, as stars fade and matter becomes locked into remnants, black holes take over as the primary entropy sinks. They become the universe's long-term memory vaults, not because they remember details, but because they permanently remove those details from accessibility. As cosmic expansion accelerates, black holes grow increasingly isolated. They consume nearby matter, but fresh material becomes scarce. Eventually, each black hole evolves alone within its causal island, surrounded by expanding emptiness for immense periods. Black holes appear eternal. But even black holes are not exempt from thermodynamics. Quantum effects at the event horizon cause black holes to emit radiation, a phenomenon known as Hawking radiation. This radiation carries energy away, causing the black hole to lose mass over time. The process is extraordinarily slow. A stellar mass black hole takes far longer than the current age of the universe to evaporate. A supermassive black hole requires timescales so vast they defy intuitive comparison. Yet evaporation proceeds relentlessly. As a black hole shrinks, its temperature rises slightly, increasing the rate of radiation. Eventually, in the unimaginably distant future, black holes disappear entirely, converting their mass into diffuse radiation. During this process, entropy does not decrease. The radiation emitted carries entropy away, and the total entropy of the universe continues to rise. Information, once hidden behind the horizon, becomes dispersed into the environment in highly scrambled form, effectively unrecoverable. This marks a transition. For most of cosmic history, black holes act as entropy vaults, storing disorder efficiently. In the far future, they become entropy sources, releasing that stored disorder back into the universe as low-energy radiation. Throughout both phases, black holes dominate the entropy budget. They shape the universe's thermodynamic trajectory more than any other object. Without black holes, the universe would still trend toward equilibrium, but the path would be less direct. Black holes accelerate entropy's rise by concentrating mass, hiding information, and later releasing it in the most diluted form possible. They represent gravity's most decisive contribution to the arrow of time. From the perspective of heat death, black holes are both milestones and mechanisms. They mark the point where matter has collapsed as far as it can, and they ensure that whatever structure remains is ultimately converted into featureless radiation. In a universe filled with stars, complexity flourishes briefly. In a universe dominated by black holes, complexity is already on borrowed time. Yet black holes do not bring about heat death by violence or catastrophe. They do it by patience. They sit, grow, merge, and wait. They lock away usable energy. They erase accessible information. They reshape space-time so that entropy becomes unavoidable. And when they finally fade, the universe is left with little more than thin radiation stretched across an ever-expanding cosmos. A universe where the deepest vaults have emptied and nothing uneven remains to drive change. Black holes are not the end of the universe. They are the reason the end can ever arrive. At the edge of a black hole, emptiness is never truly empty. Even in the deepest vacuum, space flickers. Fields fluctuate. Pairs of particles briefly appear and vanish, borrowing energy from uncertainty before returning it almost instantly. This restless quantum activity fills all of space-time, but nowhere does it matter more than at the boundary of a black hole. Here, at the event horizon, quantum physics quietly undermines gravity's most absolute creation. This is where Hawking radiation is born. For most of cosmic history, black holes seem eternal. They swallow matter, they merge, they grow, nothing escapes. Their darkness appears final. Yet quantum mechanics introduces a subtle imperfection, one so small that it takes longer than the age of the universe to notice, but so fundamental that it changes the fate of everything. Black holes leak. To understand how, it helps to picture the vacuum not as emptiness, but as a sea of fluctuating energy. According to quantum field theory, Particles and antiparticles constantly appear in pairs, existing for fleeting instants before annihilating one another. Normally, these events leave no trace. Near an event horizon, the situation changes. If a particle pair forms right at the horizon, gravity can separate them. One particle may fall inward, while the other escapes outward. To an observer far away, this escaping particle appears as real radiation emitted by the black hole. Energy conservation still holds, but with a twist. The particle that escapes carries positive energy. The one that falls in effectively carries negative energy relative to the outside universe. The black hole's mass decreases by exactly the amount needed to balance the books. The result is slow, steady mass loss. This radiation is not dramatic. For large black holes, it is unimaginably faint. A stellar mass black hole emits far less radiation than the cosmic microwave background bathing it. A supermassive black hole is even colder. Yet the process never stops. Hawking radiation is a consequence of the horizon itself. As long as the horizon exists, evaporation continues. This discovery revealed something extraordinary. Black holes have a temperature. The more massive a black hole is, the colder it becomes. The smaller it gets, the hotter it grows. This inverse relationship ensures that evaporation accelerates near the end of a black hole's life, but only after an almost inconceivably long wait. The timescales involved redefine the word long. A black hole with the mass of a star requires roughly 10 to the power of 67 years to evaporate. That is a number with more zeros than seconds that have passed since the Big Bang by an overwhelming margin. Supermassive black holes demand timescales closer to 10 to the power of 100 years. During this era, the universe is already unrecognizable. Stars are gone. Galaxies have faded into loose collections of remnants. Expansion has isolated every region of space from every other. The cosmic background radiation has cooled to nearly absolute zero. Matter, if it still exists, is locked into cold, degenerate forms or has begun to decay. Against this backdrop, black holes quietly glow, not visibly, but thermodynamically. Each emitted particle carries away entropy. The radiation is extremely low energy, spread thinly across vast volumes of expanding space. It represents the most diluted form of energy imaginable. This matters because evaporation completes a thermodynamic cycle. Black holes form by concentrating matter and information, massively increasing entropy through horizon area. Evaporation reverses the concentration, but not the entropy. The information released is scrambled beyond recognition, dispersed across radiation fields, in correlations so subtle they are effectively irretrievable. The universe remembers nothing specific. As black holes shrink, their temperature rises, and their radiation grows stronger. The final stages of evaporation are brief compared to the long wait that precedes them. The last moments release a burst of particles, still tiny by astrophysical standards, but dramatic relative to the black hole's prior silence. Then the horizon disappears. When the last black hole evaporates, something profound changes. For the first time since gravity began forming structures, there are no longer any regions of space-time from which information cannot escape. Event horizons vanish. The universe becomes horizon-free on all but cosmological scales. This marks the beginning of the evaporation era's aftermath, a universe dominated entirely by radiation and isolated particles drifting through expanding space. Black hole evaporation also answers a deeper question about permanence. Nothing built from matter and energy is eternal. Not stars, not atoms, not even space-time's most extreme distortions. Stability in the universe is always conditional, always temporary, always purchased with time rather than guaranteed by law. Gravity can delay decay. Quantum mechanics ensures it never cancels it. This insight reshapes the meaning of heat death. Heat death is not a universe filled with black holes forever. It is a universe where even black holes have finished their work, where every concentration of energy has been smoothed out, every gradient erased, every structure reduced to uniformity. Evaporation is essential to that outcome. Without Hawking radiation, black holes would lock away energy indefinitely, preventing the universe from reaching full equilibrium. With it, black holes become the final contributors to entropy's rise, releasing their contents in the least useful form possible. Radiation emitted during evaporation continues to redshift as space expands, losing energy and becoming ever more diffuse. Interactions between particles become so rare that meaningful change all but ceases. Time stretches. Events become separated by intervals so vast that the concept of before and after loses relevance. Processes still occur, but so slowly and sparsely that the universe appears effectively frozen. This is not a violent ending. No collapse, no explosion, no cosmic catastrophe. Just a patient unwinding. The evaporation era represents the last act of gravity as an organizing force. Once black holes are gone, gravity loses its most extreme expression. What remains is a universe governed almost entirely by expansion, quantum fields, and entropy maximization. Even darkness fades, not into light, but into irrelevance. Hawking radiation teaches a quiet lesson. Absolutes do not survive contact with reality. Event horizons seem final, but they are porous at the quantum level. Black holes seem eternal, but they are only very slow to die. The universe allows no permanent exceptions. Every structure dissolves, every boundary erodes, every vault eventually opens, and when the last black hole has evaporated, the universe takes another step closer to its most uneventful state, not because something dramatic has happened, but because the final obstacles to equilibrium have finally, patiently, disappeared. The last black hole fades without ceremony. No flash marks the moment, no ripple announces the end. One final packet of radiation drifts outward, stretched immediately by expansion, diluted almost as soon as it exists. With that, the universe crosses a threshold it will never revisit. Structure is finished. For the first time since the earliest moments after the Big Bang, there are no bound, macroscopic objects left that can meaningfully evolve. No stars burn, no remnants cool, no horizons hide information. Gravity still exists, but it has nothing left to organize. What remains is a universe composed almost entirely of thin radiation. Photons dominate this era, not energetic gamma rays or visible light, but ultra-low energy photons whose wavelengths stretch across astronomical distances. Each photon carries so little energy that individually they are almost irrelevant. Collectively, they define the universe's final thermodynamic character. This is not darkness in the familiar sense. Darkness implies the absence of light, relative to eyes adapted to brightness. Here, light still exists, but it is too cold, too diluted, too uniform to illuminate anything. The universe is luminous in principle and inert in practice. After black hole evaporation, matter has been almost completely converted into radiation. If any massive particles remain, they are sparse, cold, and non-interacting. Expansion has stretched space-time so dramatically that collisions between particles are effectively non-existent. Distances between particles increase faster than any interaction range can compensate for. This is the end of structure, not because structure is forbidden, but because it has no mechanism left to form. To understand why, consider what structure requires. Atoms need electrons bound to nuclei. Molecules need atoms close enough to share electrons. Planets need gravity strong enough to overcome thermal motion. Stars need gas dense enough to collapse and hot enough to ignite fusion. Every one of these conditions depends on energy gradients, density contrasts, and interaction rates. None of these survive this era. Temperature differences vanish as radiation equilibrates. Matter density falls toward zero as space expands. Even time becomes a weak concept because nothing changes in any meaningful way from one moment to the next. Chemistry is gone. Chemical reactions require collisions with sufficient energy and frequency. In this universe, particles rarely meet, and when they do, they drift past one another with energies far below any threshold required to rearrange internal structure. Bonds cannot form, reactions cannot proceed. Atoms themselves, if any remain, are effectively isolated forever. Even if two atoms happen to approach one another, expansion ensures that their relative motion carries them apart faster than they can interact. The universe does not forbid chemistry, it simply denies it opportunity. Planets are impossible. Planetary systems rely on gravitational binding within a dense environment. By this stage, expansion has stretched matter so thin that gravity cannot gather it. No region contains enough mass in close enough proximity to assemble anything macroscopic. Stars are impossible. Star formation requires cold gas clouds with sufficient density to collapse. There is no gas left, and no density to collapse from. Even if a cloud somehow existed, the universe's temperature floor, set by ever-redshifting radiation, would prevent efficient cooling. Fusion never ignites again. The universe has not just lost its stars, it has lost the conditions that make stars conceivable. What fills space now is a near-perfect thermal bath. Photons dominate, accompanied perhaps by neutrinos, electrons, positrons, and whatever stable particles survive the longest. Each species drifts independently, rarely interacting, their energies steadily declining as expansion stretches their wavelengths and momenta. Entropy is near its maximum, not because the universe is chaotic, but because it is uniform. Every accessible microstate is roughly as likely as any other. There are no preferred directions for energy flow, no gradients to exploit, no free energy to do work. This is what thermodynamic equilibrium looks like on a cosmic scale. Importantly, this state is not hot. Heat death does not mean high temperature. It means no usable temperature differences. The universe approaches a temperature asymptotically close to absolute zero, though never quite reaching it. But because every region shares essentially the same temperature, that temperature is meaningless in terms of driving processes. Motion still exists at the microscopic level. Particles still move. Fields still fluctuate. But these motions do not accumulate into anything larger. Nothing organizes, nothing remembers. Information still exists in principle, encoded in correlations among particles and fields, but it is so diffuse and scrambled that it cannot be accessed or used. There are no observers left to extract it, no memory systems to store it, no physical processes to amplify it into significance. Cause and effect blur. Not because causality breaks, but because events are so rare and so weakly connected that distinguishing sequences becomes operationally impossible. The universe does not stop obeying laws. It stops expressing them in interesting ways. Time continues mathematically, but without clocks, without irreversible processes to mark change, time loses its practical meaning. One interval looks like any other. Nothing accumulates, nothing decays in a way that matters. This is the final silence. It is not a void. It is not nothingness. It is everything spread too thin to matter. The path to this state was long and indirect. It passed through galaxies, stars, life, black holes, and quantum evaporation. Each step followed directly from the same underlying principles: entropy increase, energy dispersal, and expansion. The universe did not choose this outcome. It drifted into it because almost every alternative was statistically inaccessible. This thin radiation universe is not unstable. There is no tendency for structure to re-emerge spontaneously. Fluctuations occur, but they are microscopic and fleeting. The probability of assembling something complex from this background is so small that it effectively never happens. The universe has settled. From a thermodynamic perspective, this is the end state predicted by known physics. A universe where energy exists but cannot be used, where matter exists but cannot assemble, where laws exist but cannot produce novelty. Heat death is not dramatic, it is thorough, and in this final condition, after black holes, after stars, after atoms, the universe becomes what it was always moving toward, a place where nothing is uneven enough to change. Thermal equilibrium is not an event, it is a condition. It does not arrive with a moment that can be dated, nor does it announce itself through any observable transition. Instead, it emerges asymptotically, as every process that once produced change gradually exhausts the differences that made change possible in the first place. When physicists speak of maximum entropy, they are not describing chaos or destruction, but the complete elimination of usable contrast within a closed system. In the context of the universe, thermal equilibrium represents the final state allowed by known physics, a condition in which energy is still present, particles may still exist, and physical laws still hold, yet no further macroscopic evolution can occur because nothing remains uneven enough to drive it. This is what heat death truly means. At a fundamental level, heat death is defined by the absence of temperature differences. Temperature is not merely a measure of how hot something feels, it is a statistical description of how energy is distributed among microscopic degrees of freedom. When two systems have different temperatures, energy can flow between them, and that flow can be harnessed to perform work. Engines run, chemistry proceeds, structures form and decay. When temperatures equalize, that possibility disappears. Importantly, thermal equilibrium does not require the universe to reach absolute zero. It requires only that all regions share the same temperature, whatever that temperature may be. In an expanding universe, this equilibrium temperature approaches extremely low values, but the crucial point is uniformity, not coldness. Uniform energy distribution eliminates free energy. Free energy is the portion of energy that can be converted into organized motion, structure, or information processing. As entropy increases, free energy decreases. At maximum entropy, free energy reaches its minimum value, and no process can extract useful work from the system. At that point, physics does not stop functioning. It stops doing anything interesting. To understand why this matters so deeply, consider what all physical processes have in common. Every chemical reaction, every biological metabolism, every mechanical motion, every act of computation depends on gradients, differences in temperature, pressure, chemical potential, or gravitational potential. These gradients are the engines of causation. They determine direction, sequence, and irreversibility. Thermal equilibrium erases gradients completely. Without gradients, there is no preferred direction for energy flow. Without energy flow, there is no mechanism to drive change. Without change, time loses its operational meaning. This is not a philosophical statement. It is a physical one. Time, as measured by clocks, is inseparable from irreversible processes. A clock works because it undergoes a sequence of states that cannot be perfectly reversed. Whether mechanical, atomic, or biological, every clock depends on entropy production. It relies on energy dissipation to distinguish one moment from the next. In a universe at maximum entropy, no such processes remain. Particles may still move, but their motion produces no cumulative effect. Interactions may still occur in principle, but they are statistically symmetric and lead nowhere. Fluctuations exist, but they do not amplify. Every configuration is as likely as any other, and no configuration persists long enough to function as a record. Without records, the distinction between past and future becomes meaningless. This is what it means to say that time loses operational meaning. The mathematical parameter we call time still exists in physical equations, but it no longer corresponds to anything observable. There are no clocks to mark it, no processes to index it, no memories to store it. One interval is indistinguishable from the next, not because time has stopped, but because nothing changes in a way that can be tracked. The universe enters a state of temporal flatness. From a thermodynamic perspective, this is the most probable condition imaginable. Given enough time, any closed system evolves toward the macro state with the greatest number of compatible microstates. For the universe as a whole, that macro state is one of extreme uniformity, minimal free energy, and maximal entropy. The path to this state is long and indirect, but the destination is dictated by statistics. By the time thermal equilibrium is approached, the universe has already passed through every other meaningful phase of evolution. Stars have burned out, galaxies have dispersed beyond causal contact. Black holes have evaporated. Matter, if it still exists, is sparse and inert. Radiation dominates, stretched to wavelengths so long that individual quanta carry almost no energy. At this stage, entropy is not increasing rapidly because there is little left to increase. The universe is already near its maximum entropy configuration. Any remaining entropy production occurs at an infinitesimal rate, driven by extremely rare quantum processes or residual particle decays. Crucially, equilibrium is stable. Once reached, there is no natural mechanism that pushes the universe away from it. Any small fluctuation that produces a temporary local imbalance is overwhelmingly likely to dissipate almost immediately, restoring uniformity. The probability of a fluctuation large enough to create sustained structure is so small that for all practical purposes, it never occurs. This stability is not enforced by force, but by probability. The number of microstates corresponding to equilibrium vastly exceeds the number corresponding to any structured configuration. Even if the laws of physics allow structure, statistics ensure that it almost never appears once equilibrium dominates. This distinction is essential. Heat death does not imply that structure is forbidden by physical law. It implies that structure is statistically inaccessible. The universe has not become incapable of complexity. It has become incapable of finding it. From this point onward, entropy has won completely, not as an active force, but as a counting principle. Every accessible configuration looks essentially the same at macroscopic scales. No configuration offers an advantage in extracting work or producing novelty. Information in this context becomes a subtle concept. Information is not annihilated in thermal equilibrium, but it is dispersed so thoroughly that it cannot be localized or retrieved. Correlations between particles still exist in principle, but they are so weak and so spread out that no physical system can exploit them. Information exists mathematically and disappears operationally. Memory becomes impossible. Memory requires stable, distinguishable states that persist through time. It requires energy barriers, error correction, and irreversible transitions. All of these require free energy. At maximum entropy, none of these conditions can be satisfied. There are no observers in a universe at thermal equilibrium, not because observers are forbidden, but because observation itself is a process that requires energy gradients and entropy production. Without observers, concepts like before, after, cause and effect lose their grounding. The universe still exists, it simply has no narrative. This final condition is sometimes misunderstood as a kind of cosmic death in the emotional sense, but physics assigns no emotion to it. Thermal equilibrium is not tragic or ominous. It is the natural endpoint of statistical evolution in a system that began far from equilibrium. The remarkable fact is not that the universe ends this way. The remarkable fact is that it did not begin this way. The low entropy initial state of the universe made everything else possible. Stars, chemistry, life, consciousness, history. Thermal equilibrium is the price of having had those things at all. In that sense, heat death is not the negation of cosmic meaning, but its thermodynamic consequence. Once equilibrium dominates, the universe becomes simple again, not in the sense of being ordered, but in the sense of being featureless. Differences vanish, directionality disappears, the arrow of time dissolves into symmetry. What remains is a universe that obeys its laws perfectly and expresses them no longer. Maximum entropy is not chaos, it is silence. Not silence as absence, but silence as completion. In a universe approaching maximum entropy, the most profound loss is not energy, matter, or structure, but information. Not information in the abstract mathematical sense, which remains conserved within the formalism of physical law, but information as something that can be stored, accessed, amplified, and used to distinguish one state of the universe from another. The distinction matters because physics does not merely describe what exists, it describes what can happen, and what can happen is inseparably tied to what can be remembered. Information, in physical terms, is never free. It must be encoded in material systems, arrangements of particles, fields, or correlations that are stable against noise and persist through time. A fossil records biological history because it preserves structure. A memory exists because neural states are maintained. A photograph works because chemical or digital configurations remain fixed long enough to be read later. All such records depend on energy barriers, error correction, and irreversibility. Each of these, in turn, depends on the availability of free energy and on the presence of entropy gradients. In a maximum entropy universe, these prerequisites no longer exist. At thermal equilibrium, energy is distributed uniformly across all accessible degrees of freedom. There are no gradients to sustain ordered configurations against perturbations. Any local fluctuation that momentarily lowers entropy is statistically overwhelmed by the vastly larger number of microstates that restore equilibrium. This does not require an active restoring force. Probability alone suffices. The result is that information, while not destroyed, becomes delocalized to the point of irrelevance. From the standpoint of statistical mechanics, this outcome is inevitable. Entropy measures the logarithm of the number of microscopic configurations compatible with a macroscopic description. As entropy increases, the number of accessible microstates explodes. Correlations that once encoded specific histories are spread across so many degrees of freedom that reconstructing them becomes physically impossible, even in principle, because doing so would require reversing entropy across an astronomical number of particles simultaneously. This is why information loss in a thermodynamic sense is not about violation of conservation laws. It is about inaccessibility. Information is not erased from the universe, it is diluted beyond retrieval. The universe retains no usable record of how it arrived at its current state. Memory fails for the same reason. Memory is not a passive property of matter, it is an active process that requires continual maintenance. Whether biological or artificial, memory systems rely on metastable states, configurations that resist decay long enough to store distinctions between past and present. These systems consume energy precisely to fight the natural tendency toward equilibrium. Error correction, redundancy, and stability are all thermodynamic achievements. At maximum entropy, no such achievements are possible. Without free energy, no mechanism can sustain the asymmetry required for memory. Any attempt to store information would require creating a lower entropy subsystem within a higher entropy environment, but without gradients, this cannot be done. Even if a fluctuation were to momentarily create such a subsystem, it would decay on timescales too short to function as a record. The universe becomes incapable of remembering itself. This has immediate consequences for observers. An observer is not merely a conscious entity, but any system capable of correlating internal states with external events and preserving those correlations over time. Observation requires irreversibility. It requires that measurement outcomes be recorded in stable degrees of freedom. It requires entropy production. In a universe at thermal equilibrium, observation is physically impossible. There is nothing to measure meaningfully, no stable reference frames, and no durable records. Even if particles interact, those interactions do not accumulate into knowledge. They leave no trace. Without observers, causality loses its operational footing. Causality, in physics, is not just about equations determining future states from past ones. It is about the ability to identify cause and effect relationships through records and correlations. A cause precedes an effect only if the effect retains information about the cause. That retention requires memory, which requires entropy gradients. When records disappear, causal structure dissolves into statistical symmetry. The laws of physics remain time-symmetric at the microscopic level, but the macroscopic arrow of time vanishes. There is no longer a meaningful distinction between past and future because no process exists that can mark the passage from one to the other. Events may still occur in a mathematical sense, but they do not form sequences that can be ordered, remembered, or compared. This is what is meant when physicists say that time loses operational meaning. Time still appears as a parameter in equations, but it ceases to correspond to any measurable progression. Without clocks, without irreversible processes that tick, there is no way to operationalize time. Every moment becomes indistinguishable from every other, not because time has stopped, but because nothing persists long enough to define duration. The disappearance of records also eliminates the possibility of history. History is not simply what happened, it is what remains knowable. Geological strata, cosmic background radiation, isotopic abundances, and biological evolution all serve as records of past states because entropy increased in such a way that information was preserved locally while being dissipated globally. In a maximum entropy universe, that balance no longer exists. Information cannot be preserved locally at all. The universe has no past in any operational sense. It has no future either. It exists only as an equilibrium state without narrative. This leads to a crucial question. Could complexity ever re-emerge spontaneously? At first glance, statistical mechanics allows for fluctuations. Even in equilibrium, random deviations from uniformity occur. Given infinite time, any configuration, no matter how complex, has a non-zero probability of appearing momentarily. This fact is often cited as a loophole in heat death scenarios. In practice, it changes nothing. The probability of a fluctuation large enough to create sustained complexity, let alone observers or memory, is so vanishingly small that it is effectively zero on any physically meaningful timescale. More importantly, such fluctuations would not persist. Without an external entropy gradient to stabilize them, they would decay almost immediately back into equilibrium. Complexity is not just about configuration, it is about maintenance. A single low entropy arrangement appearing briefly does not constitute complexity in any functional sense. Complexity requires continuous energy flow, error correction, and hierarchical structure. None of these can exist in equilibrium. The universe may momentarily assemble something intricate, but it cannot keep it. This asymmetry is fundamental. While entropy increase is robust and self-sustaining, entropy decrease is fragile and transient. The universe overwhelmingly favors states that erase distinctions rather than preserve them. From an information theoretic perspective, maximum entropy corresponds to maximum uncertainty. No state contains more usable information than any other. All macrostates become equivalent in their informational content. The universe ceases to encode anything meaningful about itself. This is the final silence. Not silence as emptiness, but silence as indistinguishability. No signals stand out from background. No structures persist against noise. No correlations survive long enough to matter. The universe becomes informationally flat. It is important to emphasize that this outcome is not imposed by any specific force or law. It emerges from the same statistical reasoning that governs gas diffusion, heat flow, and radioactive decay. Given enough time, and given no external intervention, a closed system explores its most probable states. For the universe, that state is one in which all distinctions are erased. The extraordinary fact is not that complexity disappears. The extraordinary fact is that complexity existed at all. Its existence depended entirely on the universe beginning in an exceptionally low entropy condition, with enormous gradients available to be exploited. Once those gradients are exhausted, nothing in known physics can recreate them at a cosmic scale. There is no mechanism to reset the universe thermodynamically. No process within equilibrium can generate sustained disequilibrium. Without such a mechanism, complexity cannot re-emerge spontaneously in any meaningful sense. The universe does not forget because it chooses to forget. It forgets because memory requires work, and work requires gradients, and gradients are finite. In the final state, information still exists mathematically, encoded in correlations too diffuse to access. The laws of physics still operate perfectly, but they operate on a system that no longer differentiates outcomes. Everything that once made the universe dynamic, historical, and knowable has faded, not through destruction, but through completion. The silence that remains is not the absence of reality. It is the absence of distinction. Once thermal equilibrium is approached, the universe appears to have reached a condition from which no further meaningful evolution can proceed. Entropy is maximized, free energy is exhausted, records have vanished, and no process remains capable of sustaining complexity. Heat death, in this sense, looks final. And yet modern physics leaves open a narrow conceptual space for asking whether this finality is truly absolute, or whether there exist rare, speculative mechanisms that could, in principle, restart cosmic activity. Exploring these possibilities is not an exercise in optimism. It is an exercise in understanding the limits of physical law. Each proposed escape from heat death reveals something important, not about how the universe is likely to behave, but about why heat death remains the most conservative and compelling conclusion. The first category of speculation arises from quantum fluctuations. Quantum mechanics does not allow perfectly static states. Even in a vacuum, fields fluctuate. In thermal equilibrium, microscopic deviations from uniformity occur continuously. Over infinite time, statistical mechanics permits arbitrarily large fluctuations, including configurations that momentarily resemble lower entropy states. This fact leads to a tempting idea. If time is infinite, could a sufficiently large fluctuation eventually recreate structure, complexity, or even an entire new universe? Mathematically, the probability is not zero. Physically, it is irrelevant. The probability of a fluctuation capable of generating sustained complexity is so fantastically small that it dwarfs all meaningful timescales. Worse, such fluctuations would not be stabilized. Without external gradients, they would decay almost instantly. A temporary configuration that briefly resembles order does not constitute a restart of cosmic evolution. It is a statistical anomaly, not a pathway. More troublingly, if such fluctuations were the dominant source of structure, they would overwhelmingly favor minimal observers, brief, disordered configurations with false memories, rather than coherent universes with long histories. This leads to deep paradoxes about predictability and observation, suggesting that large equilibrium fluctuations are not a viable foundation for cosmic renewal. Quantum fluctuations, while real, do not rescue the universe from heat death. They merely decorate equilibrium with noise. A more radical possibility involves vacuum decay. Modern quantum field theory suggests that the vacuum state of the universe may not be absolutely stable. The energy associated with empty space, the vacuum energy, could occupy a metastable configuration. If so, a transition to a lower energy vacuum could occur spontaneously, triggering a dramatic restructuring of physical laws. Such an event would propagate at the speed of light, rewriting particle properties, forces, and constants. From within the affected region, it would not look like an explosion or rebirth. It would simply replace one universe with another. Vacuum decay does not violate thermodynamics, but it sidesteps it by changing the rules entirely. Entropy accounting depends on the laws of physics being fixed. If the vacuum changes, the meaning of entropy changes with it. However, this possibility remains deeply speculative. There is no empirical evidence that our vacuum is metastable, and even if it were, decay would not represent a continuation of cosmic history. It would represent termination followed by replacement. Nothing from the prior universe would survive in any meaningful sense. Vacuum decay does not prevent heat death. It merely ends the universe before heat death completes. Another speculative avenue invokes cyclic or bouncing cosmologies. In some models, the universe undergoes repeated cycles of expansion and contraction. Each cycle ends not in equilibrium, but in a bounce that resets conditions. If entropy could be diluted or discarded between cycles, perhaps into extra dimensions, then complexity could reappear indefinitely. The difficulty is entropy bookkeeping. Entropy is extraordinarily difficult to erase. Every known physical process increases it. For cyclic models to work, they must explain not only how contraction occurs, but how entropy accumulated over one cycle does not overwhelm the next. No empirically grounded mechanism currently succeeds at this without introducing ad hoc assumptions. Moreover, accelerated expansion driven by dark energy strongly disfavors future contraction. Observations indicate that expansion is not slowing toward a turnaround, but speeding up toward isolation and dilution. Cyclic cosmologies remain mathematically interesting, but observationally unsupported. Related ideas emerge from multiverse scenarios. In some frameworks, our universe is one region within a much larger ensemble of universes, each with different physical parameters. New universes may continually form through processes like eternal inflation, while older ones drift toward heat death. From this perspective, heat death is not the end of everything, only the end of a single cosmic domain. This view reframes the question rather than answering it. Even if new universes form elsewhere, heat death still governs the fate of any given universe once its gradients are exhausted. The multiverse does not rescue complexity within our universe. It merely asserts that complexity may arise repeatedly in disconnected regions. Crucially, multiverse models remain empirically inaccessible. By construction, other universes cannot be observed, interacted with, or tested. As a result, they do not weaken the conclusion that heat death is the most likely fate of our universe, based on known physics. One might also imagine unknown physics intervening at extreme scales. New particles, new forces, new principles that emerge only after equilibrium is reached. History warns against assuming that present knowledge is complete. Yet, this cuts both ways. Any unknown physics capable of reversing heat death would need to violate or bypass the second law of thermodynamics on cosmic scales. Such a violation would require not a small correction, but a structural upheaval of statistical mechanics itself. No existing anomaly points in this direction. Every experimental test to date reinforces entropy's role as a fundamental constraint. The absence of evidence here matters. Heat death does not rely on speculative physics. It follows directly from well-tested principles applied consistently over long time scales. This is why heat death is best understood not as a prediction, but as a default outcome. Given the laws of thermodynamics, quantum mechanics, and general relativity as currently understood, and given the observed properties of the universe, expansion, dark energy, finite matter content, heat death requires no special assumptions. It emerges naturally. All alternative endings require additional assumptions: metastable vacua, entropy disposal mechanisms, unobserved dimensions, or unverifiable ensembles of universes. Each adds complexity to avoid a conclusion that already follows from simpler premises. From a scientific standpoint, heat death is not pessimistic. It is conservative. It assumes no miracles, no resets, no hidden reservoirs of order waiting to be tapped. It assumes only that entropy behaves tomorrow as it has always behaved, and that expansion continues as observed. In that sense, heat death is not a failure of imagination, it is a triumph of restraint. The universe does not end because it breaks, it ends because it finishes. Energy spreads, gradients flatten, information disperses, structure dissolves. The process is slow, impersonal, and statistically overwhelming. Nothing dramatic is required, nothing external intervenes. Speculative escapes remain valuable, not because they are likely, but because they test the boundaries of understanding. they clarify what would need to change for heat death to be avoided, and in doing so, they reveal how deeply entropy is woven into the fabric of physical law. For now, and for any future grounded in known physics, heat death remains the most plausible cosmic ending, not because it is inevitable in some metaphysical sense, but because it is the outcome that requires the fewest assumptions. The universe began far from equilibrium. That single fact made everything else possible. Once equilibrium is reached, nothing within the universe can undo it. Heat death is not the universe giving up. It is the universe arriving where probability has been guiding it all along.